Alright, welcome to the second section for the energy unit. This one's all about potential and kinetic energy. So our purposes for this one, we are going to learn or understand what potential energy is. We're going to understand kinetic, and we're going to solve some problems involving these two different types of energy. And you're going to see that these purposes are going to repeat a lot for these sections. It's going to be understand something, solve some problems. Today, I'm also going to show you what work energy theorem is. It's not super important for what you're going to need to do for the test, but this is a pretty major theorem in physics, so it's important if you continue on that you understand what this is, and at least that you've seen it, not necessarily that you fully get it, but I want to at least show you. It's related to what we're dealing with today anyways, so it's worth showing you. Potential energy. This is simply a stored energy. There's a bunch of different examples of this. We've got chemical potential energy. This is like the gasoline you put in your car, food, batteries. Then we got elastic. This is like if you have a bow, like a bow and arrow, rubber band, trampoline. This gives you elastic potential energy. So as I stretch a rubber band, it has the potential to snap and hurt. Electrical potential energy, this is like static charge. If you've ever had it where you go to touch a doorknob or something and it shocks you, that is a potential stored energy in your body for releasing at some point. So as far as potential energy goes, we are going to focus on gravitational potential energy, not any of those other ones. This is a stored energy due to an object's position, so its height. And remember, energy can be converted. So I can convert from this potential energy to kinetic or kinetic to potential. It can be moved between any of these different ones. So it's not stuck in one kind of energy. You can transform from one form to another. So gravitational potential energy, here's your equation for it. This should look familiar from yesterday. So mass, acceleration due to gravity, height. Now a note on height. The height is measured relative to a reference point. So when I'm saying what's the potential energy, I need to give a specific reference point. So I would say above the table, above the floor, above whatever, so that you know specifically what this height is in reference to. That's the only confusing thing about potential energy is it's relative to something. And you'll see in multiple examples how that can be different. Let's do an example here. So a 10 kilogram doom slug is sitting on a 1.3 meter tall desk on the planet detritus, different acceleration due to gravity. If the doom slug is lifted 0.6 meters above the table, we want to know how much gravitational potential energy does the doom slug have with respect to two different things. One with the table, one with respect to the floor. So here's our doom slug. It's above a table. Here's the two different heights. If I want to know what is its potential energy relative to the table, when I do MGH, I want height as 0.6. So I'm needing the distance above the table. That's what I'm going to use here as H. There's your amount of joules relative to the table. So with respect to the floor, now my height is not 0.6. Now it's going to be 1.9. So I'm just adding those two heights together, and I get a different and larger potential energy because it's higher above the floor than it is the table. So that's how you can see it'll be different potential energies depending on where my reference point is. Let's move to kinetic energy. This is the energy of motion. Kinetic, kinematics, kinetic coefficient of friction. Kinetics is movement. So we can have energy because something's moving. Here's your equation, a half mv squared. This is where m is mass, that's always going to be the same. V is speed. Notice it's not velocity because kinetic energy is a scalar, so we're doing speeds, not velocities. So we've got a 2.4 kilogram doom slug flying at uniform speed of 4.2 meters per second. What is its kinetic energy? We have an equation, plug in numbers, solve it. Okay, this is very, very easy to be able to solve for kinetic energy. So now we've got an inhibitor slug with also the same mass of 2.4 kilograms. Now it's flying in the other direction. If it has 3,000 joules of energy, how fast is it moving? Same equation. Now we're just solving for speed instead of kinetic energy. So in this case, divide by a half, divide by 2.4. You get v squared is 2,500. Then v is 50 meters per second. Again, relatively easy. You're just plugging numbers in and switching things around. So now on to the work energy theorem. Again, this is a fairly important theorem in physics. So I want to show you what it is. It's just a derivation of what I've already shown you. So it's not anything new, it's just something very specific. So if a net force acts on an object, it has to be accelerating. This is due to Newton's laws. And this acceleration must be proportional to its change in EK, meaning the bigger the acceleration or the bigger the net force, the more change in kinetic energy you have. So therefore we have this equation of change in kinetic energy equals F net times distance. This is just taking my work equation, change in energy, force times distance, and making it a specific case with kinetic and F net. So you won't have this on the formula sheet, but it just makes your life a little bit easier to solve for some things. So for example, in this one, Jorgen pushes a crate full of wrinkle slugs, which has a combined mass of 150 kilograms. He pushes the crate from rest with a force of 500 newtons over a distance of 20 meters. If the coefficient of friction between the ground and the crate is 0.145, what is the final speed of the crate? Okay, a lot of information given in the question. Let's start with a free body diagram showing this wrinkle slug. Here's our forces, it's on the ground, so those two are equal. We have an applied force, and we have a friction force because it says coefficient of friction. We are accelerating because there's a change in speed, so force applied must be bigger. So here's our equation. We're going to use the work energy theorem. Change in kinetic equals F net times d. Now, F net in this case must be force applied minus force of friction. I'm told the force applied is 500. I don't know the force of friction, but you know the equation for it. So mu Fn, the normal force is equal to force of gravity, so it's m times g, and we've got the F net. Now we go back to the work energy theorem. So change in kinetic energy, this is just final minus initial, and that's equal to F net times d. My initial kinetic is going to be 0 because I started at rest, or Jorgen started at rest. So now you can plug in your numbers and solve for VF. If you need help with the algebra, again, you can come and talk to me, but this is your final velocity. You can see how you'd combine kinematics into an equation like this. Kinematics always comes back. It's going to come back in every unit. So there you go. That is kinetic and potential energy, and I will see you next video. So here we go. Here is another clip for you guys. This one's from Star Trek First Contact. One of my favorite ones because it's got the Borg in it. Anyways, yeah, so this one is another space battle one. Let's show you this one, and then you can see what you think is not correct in here. All right, give it a sec and think about what you think was not correct with that one. So with this clip, you might think, oh, I'm just repeating what I did before. Obviously, there's no sound in space, so we shouldn't have heard any of the lasers or the photon torpedoes, anything like that, which you would be correct, but that is not actually what I wanted to highlight in this one. For this one, it is... Wait, let me get to it. So everyone is shooting... It's that. That is the problem right there. Wait, I'll get you a better shot. So it's this. That is the problem. That is a laser beam that is shooting across towards the Borg ship. That is the problem. You can see it. With actual lasers, you cannot see them when they are shining. If you think about a laser pointers, you don't see anything, any laser in between from where it's being shot to where it hits the object. So really, you shouldn't see this laser as it goes across. The only time you do see lasers is when there are particles in the air. And obviously they're in space, so there's no particles for the lasers to bounce off of. Therefore, you shouldn't see the laser. So any movie that has lasers being shot, you actually cannot see the lasers from where they're being shot to where they hit. That is another misconception that, again, just ruins science fiction movies.